Hello and welcome to our lesson on regression analysis. So what we're going to do in this topic is we're going to try to wrap up, culminate what's been happening in our statistics module so far. So we started off sort of defining statistics and some terminology, and we talked about all the different ways that data could be collected through a variety of surveys or through experiments or through observational studies. Then we talked about different ways to analyze the data, different ways to organize the data, to the different types of graphs we can make, different calculations we can make. We even looked at how data could be distributed graphically, and then if we had normal distribution, we could actually figure out percentages of the data that are falling within certain markers or between certain markers. So the culminating piece here is once the data has been collected, remember the purpose of collecting statistical data is to try to make predictions, and that's sort of where we're going to be headed with what we're doing today. Okay, so let me just show you an example. Let's say that we had a classroom full of students and that I collected your heights, and as the instructor I collected your heights and shoe sizes. Okay, so let's say that the heights for people are going to be down here, and then their shoe sizes would be here. If I was to make a graph of the heights and shoe sizes for all the students in my class, what would probably happen is the taller you are, the bigger your foot is going to be. Now I know there are exceptions, right? Short people with big feet or tall people with small feet. But in general, if you're shorter, you're going to have a smaller foot, and if you're taller, you're going to have a bigger foot. And so if I was to make a scatter plot of all of your heights and shoe sizes, it would probably look something like that. Now again, you might have an outlier here or there, but in general, you're going to see this increasing data, and it's going to increase somewhat uniformly, right? So let's say the tallest person in the class was, I don't know, let's say that it's 6 feet and 1 inches tall. Okay, so 6'1" is the tallest person in the class. And I know that person who was 6'1" had a size, let's say 14 shoe. Okay, now what if I wanted to know the shoe size or guess the shoe size for someone who is 7 feet tall? Well, I don't have data from the students in my class on a 7-foot person. Or what if I wanted to know the shoe size for someone who's only 5 feet tall? Maybe I don't have data for someone who's 5 feet tall. So what we would do in a situation like this is try to create a graph that sort of mirrors what's happening or captures what's happening with this data. So you may have seen this concept before in a science class, maybe even in a math class, where you create a line of best fit. So this data almost looks linear. There's like sort of a constant increase in the data. So if we created a line of best fit for the data, even though the data stops, the line is going to keep going. And so we could use the line to, let's say we had someone who was 7 feet, we could use the line to try to predict that 7-foot person might have a shoe size that's, I don't know, 15. So I don't know what it's going to be, but this is the concept, okay? So if you have data that looks linear, you can try to create a line of best fit for that data. Now, not all data is going to be linear. It's possible that you have data that, let me see here. Instead of your data kind of increasing linearly, there are some other options. It could be that your data decreases linearly, or it could also be that the case that your data increases really fast but not linearly. So you could have data that sort of starts to increase and then really climbs, where that's not a line, or it could decrease in the same way. It starts to decrease really fast and then kind of flatten out. And graphs or data that sort of looks like this, we're going to call exponential. Okay, and again, if you were decreasing sort of constantly or increasing sort of constantly, then you would have data that we would call linear. And these aren't the only ways data could behave. These are just two types of equations of best fit that we're going to be looking at calculating in this section, because these are really common behaviors for data. Data can start to climb really fast, flattens out, climbs really fast, or decrease really fast, or just kind of increase linearly or decrease linearly. So these are two common types of equations of best fit that we're going to look at calculating today. And when we calculate an equation of best fit, we are calculating what we call a regression model or regression equation. So the topic that we're looking at today is called regression analysis. So regression analysis, it's the process of estimating the relationship between two variables. Okay, so like what's the relationship between height and shoe size? Is it a positive linear relationship? Is it a negative exponential relationship? What kind of relationship exists there? And so when the data that you're looking at, when it appears to follow the pattern of a specific type of function, as I mentioned, linear and exponential, those are two types of functions, then we can use technology, namely in this case we're going to use Desmos, to calculate a regression model or a regression equation. Those are sort of interchangeable terms there, to try to fit the data. We're going to calculate that model, that equation, in that format to fit that data. So when you create a line of best fit, you're going to create what we call a regression model, a linear regression model, or a linear regression equation, or again, exponential is an option too. And the purpose is to make predictions for values that we don't know. So for values that extend beyond the data set that we have captured. Okay, so the purpose is to make predictions. Now, I can ask my technology, my Desmos, to calculate a linear or an exponential regression for any set of data, and it may not be accurate. So I could, for example, collect data, and let's say my data is just all over the place, where it doesn't look like it's following any particular pattern. I can still ask it to create a line of best fit, but that line of best fit doesn't really capture what's happening like it did here. Okay, so how am I going to know when I calculate my line of best fit or my exponential model of best fit whether that's really a good model, whether the line that we've drawn or the exponential model that we've drawn, does it really model what's happening in the picture? In order to determine the accuracy or the reliability of the model that we're going to calculate, we're going to look at something called the correlation coefficient. So correlation is used to determine the strength of the relationship. It's also going to tell you how accurately the model will make predictions. Are these going to make accurate, reliable predictions, or is it not? Is it actually a line that represents the data, or did we just ask the calculator to do something for the sake of doing it when there isn't really a connection in the data? So we're going to look at something called a correlation coefficient, and that is going to be represented by the variable r squared. Again, that's going to be used to judge how good our model is, how closely aligned to the data it is. And r squared is always going to be a value from -1 to +1, where -1 is the lowest it could be and +1 is the highest it could be. So if you're at -1 or +1, you have the absolute lowest or absolute highest. Those are the strongest possible correlations possible. So if you have a negative correlation, that just means that your values are decreasing. If you have a positive correlation, that means that your values are going to be increasing. Okay? So on either end of this item, you have really strong correlation. So if you are at a -1, -1 here, that is the strongest possible negative correlation. If you actually had a correlation of -1, you could think about it as a percent. So 1 would be like 100%, right? On the negative end just means you have data that's decreasing, but a correlation of 1 would be like 100% match. That means your data is exactly on the model that you've calculated, and negative just means that it's decreasing. Same thing for positive. Okay, if you had a +1 for your correlation, that means your data is increasing and your data is on the model. There is an exact match there. So the farther away you get from 1 or -1, or the closer you get to 0, the weaker your correlation is. So anything in the negative just means your values are decreasing. Anything in the positive means that your values are increasing. The closer you are to 0, the weaker the correlation, and the closer you are to 1 or -1, the stronger. So you're going to get stronger as you go this way, and you're going to get stronger as you go this way, or weaker as you're getting closer to 0. Okay, I've just highlighted all over the place. So a correlation coefficient closer to 0 implies a weaker correlation, a weaker relationship, a weaker model, data that is farther from the model than we want it to be, and that means your predictions would be less reliable. Whereas if you're closer to -1 or 1, then you have a stronger correlation, you have a stronger model, you have data that's closer to the model that you've created, and your predictions are going to be more accurate and more reliable. Okay, so let's just look at some examples of how data could be falling on your graph here on your scatter plots. And these are all linear examples, but we'll see some exponential in a bit. So this would be a perfect positive correlation here. So you might have an r² value of 1 because it's perfect. Now, in the next graph, you can see it's sort of like height and shoe sizes might be. You still have a pretty strong positive correlation, but if you were to put a line of best fit in there, you have points that are not going to be exactly on that line. So here your r² value might be like, I don't know, 0.96, and I'm really just making that number up. But the farther away from your line of best fit those points are, the weaker the correlation is going to be. So this correlation in the next picture is still positive, but the points are a little more spread out. So your r² value might be like, I don't know, 0.75-ish, maybe even less. And then in the next one, you can see the values are all over the place. So there really is no correlation. I could draw a line of best fit, but which way is more accurate, I don't really know. And so here, when there's no correlation, you're going to see an r² value that's pretty close to 0. Now here you have a negative correlation, but it's kind of weak because of the values there. You can see them decreasing, but they're kind of far from the line that you would draw, your line of best fit you would draw in there. So maybe, and 0.75 is maybe a little high. Let's call this like a 0.5-ish over here. And then here we would say this is maybe like a negative 0.5-ish. And then this would be a little stronger. You can see the points would be closer to the line that you might put in there. So we can call this one maybe like a negative 90-ish. And again, just negative because it's decreasing. And when I said 90, I meant like a 90%. I like to think of these correlations as percentages. And I don't know, 96 was kind of random. Let's go back to like a 9 here. Okay, and then a perfect negative correlation. These points would be perfectly aligned here. That's the strongest relationship you can have in the negative direction. So here you'd have an r² value that would be at -1. Okay, like 100% match to your data and your model. Okay, so again, the two types of regression that we're going to focus on are linear and exponential. So linear regression is commonly used for values that tend to increase or decrease at a constant rate. And a common form of a linear function, maybe this looks familiar, is y equals mx plus b. Maybe you've seen y equals mx plus b before. It's looking like a little bit of algebra. If that scares you, I apologize. Okay. And then exponential regression is commonly used for values that increase or decrease by larger and larger quantities really rapidly. So if you start to see the graph is kind of flat and then it shoots up, or it starts to decrease and then flatten out, then an exponential model might be more appropriate than a linear model. And a common form for an exponential function is y equals a times b to the xth power. There's that exponential piece. Okay? So these are the two we're going to focus on. How does it work, though, when we want to create our regression model? So what we're going to do is use Desmos. We got to love the free Desmos app. I don't know about you, but I do. From our graphing screen, we're going to click on the plus sign that we're going to see in the upper left-hand corner. So we'll see a plus sign in the upper left-hand corner of the Desmos screen. And then from that plus sign, we're going to have some options. What we want to do is add a table. Like we did earlier when we were calculating statistics, we're going to add a table, but this time we'll be able to fill in two columns because we're going to have two different variables like heights and shoe sizes or just x's and y's. So we're going to enter that data into that table, filling in both columns, and as you're typing in the data, it's going to create a scatter plot for you. Okay, so it'll create a scatter plot. And if you really want to get a good picture, remember we have this zoom fit button. So if you don't see your scatter plot appearing, then hit that zoom fit button to automatically zoom on your data. Okay. Now in a separate line, so we're going to be entering our data in the first line here. In a separate line, so we're in a separate space here, we're going to either want to calculate a linear or an exponential model. And sorry, I'm just going bananas with the highlighter here. If we want to calculate a linear model, we're going to be going off of the y equals mx plus b concept. That's our linear concept. But a couple things about it. We don't want to use the equal sign because this isn't going to be generally exact. Generally, it's going to be a little deviated. So we're going to use the tilde in place of the equal sign. This is like we're approximating a line. Okay, so the tilde replaces the equal sign. And when we calculate our model, we want to make sure the model is connected to our data. So if you look in the table of values, instead of just x and y, it's x1 and y1. So to connect our model to the data, we want to call this x1 and y1. Okay, so it's y sub 1, it's a little subscript of 1, and then x sub 1, again a little subscript of 1, so that our model is connected to our data. All right? And then for exponential, remember the model is y equals a times b to the x power. Again, we want to use the tilde in place of the equal because we're approximating a model for the data. And to connect the model to our data, we're going to put in a y1 and an x1, y sub 1, x sub 1. And oftentimes we're going to actually calculate both models for our data, and we're going to see which one is more accurate, which one fits better. So if you're trying to determine which model fits better, then you're going to type both models into separate lines, and then you're going to compare the correlation coefficients. And so the regression models are going to also show up with your data, and it's all color coded so you can see what's what, and you can also tell how well it's going to fit. So if you look at the example that I've been highlighting over and over here, I've got some data in there, and I've got a linear model that's in black, and then I have a exponential model that's in red. And I mean, it looks like the data really could go either way, so I'm not sure if a linear model or an exponential model fits it better. So what I have to look at to be sure is the correlation coefficient. And what's going to happen when you type this into Desmos is it's going to tell you the correlation coefficient. So in both of these, you're given the correlation coefficient. So here at a 0.9837 and here at a 0.9789, this is stronger because it's closer to 1. So once I've calculated both and I look at those correlation coefficients, I can determine that this model is going to be better. So if I asked you to calculate a model, then I want to go with linear because it's got a stronger correlation. And remember, a linear equation is supposed to be y equals mx plus b. What they're going to do here is what Desmos is going to do for you is going to tell you what m and b should be in your equation. So this model would be y equals about 2.77 for m. Sorry, that's going in for m, and then so y is coming down, right? X is coming down. We're just going to replace m with what they give us here, and then we're going to add b, which here tells us is about 1.57, and that would be the linear regression model for this data. Now, if the exponential model had been better, then instead of a b to the x, right, y equals a b to the x would be an exponential model. We would replace a and b with the values they give us for a and b. So we'd say 15.25-ish times 1.07-ish to the x power, and that would be an exponential model for this data. Okay, but we would go with this one because the correlation was stronger. So let me just, again, clean up my mess. And now we're going to practice this. We're going to take some data, try to figure out which model better represents the data, and then write the model for it. Okay? So that's just an example of what you're going to see. Let's try it out ourselves. So in Desmos, we're going to hit the little plus sign, add a table, and type our data in there. So 1, 5, 8, 11, 15, 20, 25, and then 3, 12, 15, 24, 35, 39, and 50. Okay, so I'm going to hit my zoom fit button, and now I can see all the data appear on my screen. And I mean, it looks kind of linear to me, but I don't know, maybe because it's zoomed in, I can't really see the exponential properties happening there. So let me ask my calculator to calculate both models, and I'll compare and see which one's better. Okay, so I'm going to put in y, and a subscript you don't actually have to type. If you just press 1 after y, it will automatically subscript it for you. Then you're going to go to your ABC keyboard here to get your tilde. It's on the bottom row, so tilde, and then I want m, and then I want x, and again a subscript of 1 to connect it to the data I've put in, and then a plus, back to my keyboard, b. And if you've typed it all in there correctly, it's going to give you everything you need. So we have an r squared at 0.98, which is pretty good. Okay, so let's compare it now to the exponential. So we have y1, and then again the tilde, that little squiggle is called a tilde, and then we want a, and then parentheses, b, parentheses, and then we want to raise that to the exponential, right? X to the power. So x, and then we want it to be a sub 1. If you don't put those subscripts, you're going to see it's not going to calculate anything for you. Now, if we look at r squared here, r squared is 0.9115, and that is weaker than 0.98. So we want the number that's going to be closer to 1 or negative 1 if they were negative, and so the linear model is going to be better. So I'm going to choose the linear model here. And let's see. Just so we have good notes, for the linear, we had r squared at 0.9844, and for the exponential, we had r squared at 0.9115. So we're going to go linear here, okay? So the linear model is going to have us use the m and b. So for the linear model, m was 1.96, and then b was about 1.63. It doesn't really matter where you round. I usually just go to the hundredths place. So our model is actually going to put those together, and we're going to say y equals 1.96x plus 1.63. So that is our linear regression model, or we could also call it the line of best fit, or we could say it is the linear regression equation. There are lots of names for that. I didn't realize I already named that over there. So there it is. Okay, now let's just try it one more time, and if you feel good about it, you want to pause the video and give this a shot on your own, that would be wise. Now, save yourself some work too. Like, you've already typed all this stuff into Desmos. No need to retype it. If you just go back to your table now and delete out the data that you put in there, then you can just start from scratch with your new data and not have to retype all that stuff. So that's kind of how I like to roll. We got 1, 2, 4, 6, 8, 9, and 12, and then 1, 5, 17, 70, and you can see these numbers are starting to climb a lot faster, and that's kind of telling me this is probably going to be exponential, but I'm not going to assume anything. So let me zoom fit. And yeah, you could see it. Look at that data clearly is going up. It's following that red exponential curve. And that's why if you look at the correlation for the linear model, r squared is kind of weak, right? About 0.55. And then here for the exponential, r squared is equal to 1. That's an exact match. And you can see that on the graph. So that model is a perfect match for that data. Okay? So for linear, how did I write this here? For linear, r squared was about 0.5525, and then for exponential, then the r squared was 1, which is obviously as good as it's going to get. So we're going to take our exponential model. And for the exponential model, we're going to use a and b this time. So a they're giving us is about 1.01. B is saying it's about 1.998. I don't want to round it all the way to 2, so I'm just going to keep an extra decimal there. So we're going to put these together and say that our model is y equals a, which is 1.01, times, in parentheses, b, which is 1.998, raised to the xth power. So that is our exponential regression model, or an exponential regression equation, or an exponential, not a line, but an exponential curve of best fit. So lots of different ways to name that. Okay, and just to be extra clear, because our r squared is so good here, this is going to be a strong positive correlation. And because it's a strong positive correlation, then we know that we're going to have accurate and reliable predictions. The model will make reliable, accurate predictions. Reliable, accurate predictions. Okay, and the same thing here. This is going to be a perfect positive correlation, which means this model is going to make perfect predictions, okay? Very accurate predictions. Whereas in this second one, if we had chosen to use the linear model, which we absolutely could have, we could have used a line. It just would mean that when we make predictions, they're not going to be as accurate because the data doesn't really follow that type of model. Okay? So hopefully that makes sense. I know we haven't actually gotten to the making of predictions part. I'm saving that for the next topic because I feel like so far it's been enough information for this one. So hopefully the practice will get you started on just calculating the models, and then we get to the next topic, we'll talk about actually using the models to make some predictions. All right, so you've got stuff to work on, but as always, if you need some extra help, then just reach out. All right, guys, take care.